In this lecture, we'll continue to introduce the planetary scale waves using shallow water equations. So again, I like to repeat these slides that I used before. So why we can use shallow water equation to describe the atmospheric waves. So one way to show this mathematically is to start from the PE equation for the atmosphere. So the equation set of equations on the left-hand side, this is linearized horizontal momentum equations, continuity equations, and the thermodynamic equations. So through normal mode decomposition to decompose the variables into horizontal and vertical structure functions, we are able to derive the set of horizontal momentum equations for and the vertical structure equations that actually give rise to the continuity equation, and the thermodynamic equation becomes the form of mass continuity. Okay, so for each eigenvalue, which is derived by the separation constant in the decomposition between horizontal and vertical structures. So the mathematical similarity of this set of equations to the shallow water equations mathematically is identical. The only difference is the depth of the shallow water in the shallow water equation. In the atmospheric decomposed set of equations, it is the eigenvalue, and we call it equivalent depth. So this is mathematically, dimensionally, it is like the depth of a particular vertical mode. So for each vertical mode, the set of shallow water equations applies. So this is the reason, a basic consideration, we can use the shallow water equation to describe the planetary scale waves. And we use shallow water equation because it's simple and it is possible to solve the analytical solutions. So last time we used the shallow water equation to derive the planetary scale waves in a channel flow. You can think about this as a tropical channel. So the water is confined between a tropical belt, okay, say at the equator, and a northern latitude with the width of the latitude belt L, okay, and then in a constant rotating plane, okay, the set of shallow water equations are solved, and then the solutions consist of inertial gravity waves and the cavern waves. This is the dispersion relation, dispersion diagrams for the wave frequency as function of wave number, or wave number as function of wave frequency. So the curve, set of curve for n equal to 1, 2, 3 are the eastward moving and the westward moving inertial gravity waves. Here, the wave number is shown by the horizontal x-axis, and for the positive x, it is for the k wave number larger than 0, and for the negative axis, x-axis, it is for the wave number, zonal wave number less than 0. And the y-axis shows the frequency. So the set of equations consists of inertial gravity wave and the eastward moving Kelvin wave at the southern boundary and the westward moving Kelvin wave at the northern boundaries. So by extending these tropical channels to a real atmosphere in the equatorial area, we 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 adopt equatorial channel with F replaced by a beta y. So now the rotation is not constant anymore. It's a function of y. Okay, so this is normally called the beta plane approximation. So using the same set of shallow water equation, but in a beta plane with the boundary condition uh, that is because of the limit of the beta plane, because this is an approximation for the Coriolis parameters in the equatorial region. So for for the area or latitude beyond tropical belt, the F the beta plane approximation is not valid anymore. So the shallow water equation has to be solved in the equatorial belt only. This can be done by requiring u, v, and phi to be bounded as y approach to infinity. So this is actually the lateral boundary condition for the set of shallow water equations. So this approach was first adopted by Professor Matsuno in his seminar paper, Quasi-Geostrophic Motion in the Equatorial Area. So the following discussion is based on these seminar papers. So, so this set of equations contains uh, form of waves, not including inertial gravity waves, Kelvin waves, and also Rossby waves. The Rossby waves arise because in the beta plane, the Coriolis force changes in latitude. So the Rossby wave is mostly due to the conservation of absolute vorticity. So the change of planetary vorticity beta or F make the way any Mariano flow to 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 be changed to be changed under the constraint of conservation of absolute vorticity. So that produce oscillatory wave motions. So this Rossby waves is a low frequency waves, and which is more important in the for the planetary scale waves in the tropics. So I'm only to give you a brief uh, introduction to the key steps and the concept behind the mathematical derivation. So from this set of shallow water equation, first you can non-dimensionalize a set of equations by introducing the length scale square root of C naught divided by beta and the time scale square root of beta C naught, the inverse of this value, and the velocity scale by C0, which is gravity wave speed, and the phi is C squared. So here, C naught is gravity wave speed, and square root of 2C0 divided by beta is E folding length scale. That will as well show the solutions of the waves in the equatorial beta plane is exponentially decaying in the Mariano direction, and the E-folding scale is defined by C0 divided by beta and square root. So in atmosphere, the gravity wave of the first baroclinic mode, the C such C naught equal to 50 meters per second, and the beta is 2.1 times 10 to the minus 11. So this E-folding length scale is about 2,000 kilometers. That means in the equatorial atmosphere, the the equatorial wave is actually confined in the equatorial area. That means its amplitude decays in y, and the E-folding scale is about 2,000 kilometers. And in the oceans, the first Berkelian mode, the gravity wave, is only 2.5 meters per second. So the E-folding scale is very narrow. It's about 50 kilometers. So that's the reason in modeling equatorial waves, you have to have very fine resolution in the meridional direction to resolve the equatorial waves. By using this characteristic length scale and time scale, you can non-dimensionalize the shallow water equations into this set of non-dimensional form. Then you can assume the solution of the variables as sinusoidal and propagating in the zonal direction, and in the meridional direction, because we don't know how the meridional structure will be at this stage. So we simply assume they take the function of y only. Okay, and then you introduce this, substitute this waveform into the set of equations. Then you obtain this governing equations for the meridional structure, U, capital V, and capital Phi. Okay, and then through algebraic manipulation, you can rewrite this three equation into this three forms. So you express the zonal velocity and meridional velocity. These are all function of y only as a function of v. Here v is the meridional part of the solution we assume. So for the v, you actually derive a differential equation, v the second derivative in y times this set of variables in the bracket. Okay, so this differential equation happen to be a very famous and well-known equation in quantum mechanics. So that we know that the solution of this differential equation is spatial function called the parabolic cylinder functions. And for this set of for this particular differential equations, this omega square minus k square minus k over omega cannot be arbitrary numbers. It has to be an eigenvalue, 2m plus 1. And the solution of V has this form in the, it can be a function of Hermite polynomial in Y for different m, and also times exponentially decaying form e to the minus y square divided by 2. Okay, so once you have this v solved in this form, then you can substitute back into u and phi, and then you can obtain u prime, phi prime, and v prime. So this is the solution for the shallow water equation in the equatorial beta plane. Okay, so this particular eigenvalue 2m plus 1 and for kind of constraint for this omega square minus k square minus k over omega is actually the dispersion relation for this set of equations. So we're starting from the dispersion relation. You can rearrange it and express the equation in the form of function k as a function of omega. Okay, here m equal to 1 integer 1, 2, 3, and more. So, and for this set of dispersion relation, the value within the square root must be positive. So this requires omega square plus 4 omega square uh, inverse of this value minus 2m plus 1 must be positive. So then this consists of two range of frequencies. One is the higher frequency, omega must be larger than the variable square root of m plus 1 divided by 2 plus square root of m divided by 2. So the lower bound of this value is for m equal to 1. So it turns out that omega must be larger than 1.71. This is non-dimensional frequency. Another frequency range is the low frequency. Omega must be smaller than this square root of m plus 1 divided by 2 minus square root of m divided by 2. So the upper bound of this value is for m equal to 1, and that turned out to be 0.29. Okay, so for the higher frequency, we'll show later, this corresponding to the gravity waves, and for the low frequency part, it corresponds to the Rossby waves. So we can start. So in this lecture, we discuss this low frequency solutions. So for the low frequency, that omega will be smaller than 0.29. So the omega square must be much smaller than the inverse of omega square. So for this relation, you can drop the omega square. So the dispersion relation can be approximated by this square root 1 over 4 omega square minus 2m plus 1. Okay, and this dispersion relation can be rearranged into as a omega as a function of wave numbers. Okay, so if you divide the k over here, omega divided by k, that's the phase speed. So this becomes km squared plus 2m1 plus 1. So this is actually if you, this is a non-dimensional form. If you write this in a dimensional form, it is actually the phase speed equal to minus beta divided by this zonal wave number square plus beta divided by c0 minus 1, and then times 2m plus 1. So this is familiar dispersion relation for the Rossby waves. Okay, so so for the dispersion relation, in the dispersion diagram is actually shown in this diagram, and we can introduce the different mode of waves. Today we are looking only for the Rossby waves. So, but for these two frequency ranges, for the higher frequency, so the omega must be larger than 1.7, like the y-axis is frequency, and this is 1.71. So the higher frequency, these are the familiar inertial gravity wave, similar to the one we derived based on the channel flow in constant rotation coordinate using the shallow water equation. For the lower frequency range, so the frequency must be smaller than 0.29. So this is a 0.29. So for the low frequency, this dispersion relation gives you this set of dispersion, and this is the Rossby wave. If you look at the solutions, so for m equal to 1, the equatorial Rossby was shown on the left figure, and m equal to 2, the Rossby wave. So m is the for corresponding to the specific Hermite polynomial. So for m equal to 1, that means there's one nodal point. Here, the nodal point for meridional velocity is at the equator. So you see the meridional velocity is 0 at the equator, and it is asymmetric. That means v is in the northern hemisphere is equal to minus v in the southern hemisphere relative to the equator. So this is the antisymmetric for meridional flow. But for the zonal flow and for the geopotential height, They are symmetric with respect to the equator. So the Rossby wave is propagating westward, and this is m equal to 1 Rossby waves. And the x and the y is non-dimensional by the characteristic length scale. And then for the m equal 2 Rossby waves, you can see for Mariano velocity, there's a two nodal points. One is about non-dimensional y about at 1 and the minus 1. Okay, and then the y, the Mariano velocity is symmetric with respect to the equator. So they are having the same sign at the northern and southern hemisphere. But the zonal flow and the geopotential height is asymmetric with respect to the equators. So these are the animated wave solution for the Rossby waves. We'll stop here today.